Nechmia, for the invitation. This is my first time in Michigan. Everyone replies like, seriously? Yes, seriously. I've never been to Michigan before. And you know, I know many people here, so it's a great pleasure to be here. And congratulations, Nechmia. All right, so I'm going to talk about some recent results we have in oops, it's not working. Nechmia, what did we do? It works. Okay. And now we're okay. Echo again. Okay. Perfect. All right. So the research that I'm going to show falls at the intersection of these three seemingly distinct areas. So I'm going to spend a little bit of time going through each of them and emphasize the strengths and limitations to kind of understand why I want to be here at the intersection. So most of us here are actually control theorists. So we know that in control theory, we usually deal with what I would call realistic dynamics. We describe system by continuous state, continuous time, differential equations, sometimes PDE, sometimes in discrete time. With particular relevance to this talk, I'm going to assume the dynamics are on this form, which again should not be, those of you working in mechanics, you know, they're not restrictive. Most mechanical systems, our robots, our cars, can be actually modeled like that. There is a drift, and controls act along some control directions, which I can capture in that matrix. Most of the time, we want to stabilize the system somewhere, right? Stability is like 80% of what we do in control theory. And if we're more sophisticated, we want to do that optimally. We want to stabilize some system while minimizing some cost. And I would say that the limitation in control theory is that we lack expressive specification languages. And some of you here don't need any convincing here, but again, we only talk about convergence or maybe invariance, sometimes even safety. However, in formal methods, we have expressive formal specification languages. In formal methods, which again is an area in computer science, you can more or less formally express whatever you can say in plain English, in natural language. And here's a very simple example from robotics. Think of a very simple robotic environment where the environment is partitioned, and you have a robot that can move from some base, and it can gather data from some region. It has to avoid the dangerous region. It has 2 recharge stations. There's some intersections in there. I can literally write down a specification like that, and I can easily formalize it in some logic. This particular logic is called LTL, linear temporal logic. Most of you recognize here, I guess, the Boolean operators, conjunction, negation, implication. These weird symbols are temporal operators. So we can actually reason about how truth value of statements change over time, right? So we have this rich specification languages. We also have algorithmical computational approaches for verification and synthesis. That particular logic that I showed you before, LTL, has the property that I can take a formula and I can generate an automaton which accepts exactly the language that satisfies the formula. Think of some FSA, or it can be a more sophisticated FSA, like a Buki automaton or Rabian automaton. And if this is your system, if you have a finite dimensional system describing the behavior of some computer program, there is a well-defined notion of compositionality between these two. And actually, you can map a verification or a synthesis problem for a very simple system like this from a very rich specification to some game on a graph. And this problem is very well understood. We had some discussion today during my meetings that, you know, this problem is very well understood, but it's also extremely expensive. But, you know, at least we understand how to do this. And also, you know, what we have in formal methods, we have formal ways of composing systems. So my plant doesn't necessarily have to be one system, but it can be the composition of several agents interacting with each other. We know how to compose them. So that's what's nice about formal methods. Limitation, again, but traditionally, at least, it was made to be interpreted over finite state systems. Think of you write down a mathematical model for like a small computer program, right? Think of the states as being the value of the program counter, and then you can jump around, and you have a finite graph. Machine learning, we all do machine learning. We all have to do machine learning right now, so you understand this area, right? In machine learning, what the main strength in here is that we know how to deal with unknown, uncertain systems, data-driven systems. And I guess we agree that at least in classical machine learning, the main limitations are the lack of interpretability, the lack of correctness guarantees. Should we start a discussion on this or? Okay. So the interesting things happen in the pairwise intersections. Like if I'm looking in between control theory and formal methods, I can talk about a problem which also received a lot of attention in the past, I don't know, maybe 15 years, like controlling dynamical systems from rich specs, right? So I'm taking the realistic dynamics that we use in control theory, and I'm using a specification from formal methods. Can I solve this problem? Yes, and there's many approaches to solve this problem, so I don't want to go into that. I think the most popular one and the most intuitive is to take the system and discretize it. Cut it into pieces, construct some sort of a finite quotient, and then once I have a finite quotient, I know how to deal with this sort of rich specifications. The intersection between control theory and machine learning, coming from machine learning side, there's reinforcement learning, which I assume most of you are familiar with. I don't know much about my system, but I can apply actions, I can observe results, I can give rewards to those results, and based on those rewards, I can kind of learn about the environment, and I can actually develop a control policy at the same time.
Can you make sure the screen is sharing? We got someone on Zoom saying that it's not shared.
Nishmi? Just get the new chair professor doing all this.
Nice professorship that you got.
She deserves one. I mean, promote her to IT.
It's the next step. I'm actually getting the wrong one on Zoom. Is that okay?
I think that's okay. Zoom people should suck it up and do
I
that.
can try to fix that as well.
I think that's fine.
Okay.
People on Zoom, okay? Can you guys hear me? Are you okay with looking at my presentation screen? Okay, getting the wrong one. Is that okay? Oh, that's okay. That's the closed captioning. Can somebody talk to somebody on Zoom and ask them if they're fine?
Maybe try one other thing.
No, it's good.
Been knowing her since she was a grad student, actually. Yeah, Nishmi. Okay, good. So, all right. So going from machine learning to control theory, we have reinforcement learning, which we're familiar with. Now, more from the control theory side, I think the closer you get, if you're control theorist, the closest you can get to machine learning, if you're like in the traditional control theory realm, would be adaptive control, right? So in adaptive control, you have some knowledge of your system, but not complete knowledge. The most traditional way to insert uncertainty into a control system in adaptive control is to assume that they have some unknown parameters acting along some known control directions, which you can capture in that matrix F. And then you don't know the parameters, but somehow you want to get estimates, better and better estimates of the parameters, and construct a feedback controller which uses the measured state. So you assume you can measure the state and use the current estimate of the parameters to develop a control that you apply to the system. And the hope is that using this, you can stabilize the system. And also, ideally, you have the parameter estimates converging to the true values of the parameters, right? That's adaptive control. The intersection between formal methods and machine learning. There is some work on verification of neural networks. I guess we're all familiar with neural networks. Some people try to see whether they can actually have some formal guarantees for those complicated systems. temporal logic inference, there's something that I'm particularly interested in. You basically, rather than just classifying data using some hyperplanes in some high dimensional space, we use classifiers that are actually interpretable because we can write them as temporal logic formulas. So literally think of looking some executions of the system, and let's say in the simplest case can be offline supervised learning. So you have like a set of bad trajectories, a set of good trajectories. I want to build a classifier that I can actually read and I can formalize. And if I can formalize it like that, you might also imagine that I can link it to my formal synthesis problem, formal verification problem. Like I'm looking at the environment, I learned something that I can express in a formula, and then I can compose that with my specification or my robot to do, and then compose them and then develop a control strategy. There's something that I'm going to come back in this talk a little bit is I can maybe use these types of specs to make reinforcement learning a little bit better. And I'm going to come back to this. Like, for example, you know, I want to teach a robot how to drive a stick shift, right? So I want to tell the robot, okay, you got to push the clutch in first. Europeans understand, I'm not sure about the other people, but there is a clutch. Push the clutch and then engage. So you have to tell them clutch first, then engage, then gas, right? So I can put that in a specification like that. So when the robot goes into the car, it already knows that it shouldn't like try to push the gas with if the engine is not engaged. Okay, so I'm going to have 3 motivating examples in this talk. 2 are from manipulation, 1 is from autonomous driving. And again, please feel free to stop me anytime so we can discuss. So the way I organize this talk, I'm going to start from like the control theory world and go into the machine learning world. So I'm going to first assume that I have perfectly known dynamics, and then I'm going to assume that there are some unknown parameters in my dynamics. Then I'm going to assume that I have some knowledge about how the model should look like, but I don't really know the model. And at the end, this is kind of fully blown machine learning where I don't know anything about the system. Can I still have some sort of formal guarantees? Hi, no problem. Okay, so I'm going to start with this. And the example that I'm going to use is from autonomous driving. This is actually a problem that we looked at when I was Motional is a autonomous driving company. It's in Boston. So here are some realistic dynamics for the car, for the ego, right? That's the car that we're trying to drive autonomously. The goal is to follow some given trajectory. Think of I want my ego to stay in to follow the middle of the current lane. And I have state limitations such as limits on steering angle, vehicle speed. I have control bounds, like very tight physical bounds on jerk, steering. I want to minimize the energy while moving from one point to another. And I think the most interesting part is that I also want to satisfy a set of rules. And I'm showing rules that are at the top, and they should kind of more or less make sense, right? I want to avoid pedestrians, other cars. I want to satisfy speed limits. I want to stay in the lane and so on. So how do I solve this problem? So first of all, I want you to know that it kind of falls into the intersection that I showed you before, because I have realistic dynamics here. Here are we wearing our control theory hat, versus the specs here. They don't a set of prioritized rules. That's not something that we usually use in control theory. So okay, I'm going to come back to this movie. I'm going to show you how it works. So what I'm going to do, the approach that I'm going to have is, so first of all, I have to follow a trajectory. What I'm going to do, I'm going to assume it's made of a bunch of waypoints. So following trajectory would be convergence to each of one of them sequentially. So I'm going to use the notion of convergence to achieve this. And if you look at those rules, they're more or less all of them safety, right? I want to make sure something bad never happens. I don't want to ever get too close to pedestrians. I don't want to ever get too close to other cars and so on. So let's look a little bit at convergence and safety.
Professor, can I understand that the last constraint has some overlap with the state limitations?
This and this?
The last one and the second.
This one?
Yes.
Overlap to state limitations?
Yes.
Yeah, it does. right? So I can say that, for example, I cannot. So again, this already implies a little bit of a control jargon here because I have state and control. What is state and control? It depends on how you model your system, right? Apparently, steering angle is part of my state, but the derivative of that is going to be a control. But they both have limitations, right? There's a limitation, a physical limitation of how much I can accelerate and brake. There's a physical limitation of how much I can steer to. But I guess not your question. Your question is that this overlap with this?
Yes, I mean.
Yeah, that's perfectly fine. They do overlap. They do overlap, but it's natural to give them separately. Is that good?
Yes.
Okay. All right, so convergence first. And again, some of you have seen this 1,000 times before, but I guess just for clarity, and I'm going to do this very quickly. We're going to use control Lyapunov functions. So for this kind of systems, which we call affine control systems. So again, there is a drift, there is a matrix of control directions, we have control bounds. The question is, can I come up with a sufficient condition for a controller that ensures that my system globally, exponentially, in this case, converges to the origin, which again, that origin is going to become waypoints for some translation. And the answer is yes, we have such a sufficient condition, and it's based on the notion of a control Lyapunov function. That's the definition for a control Lyapunov function. If I have something like that, then any controller U that satisfies the control bounds and this inequality is going to ensure that I have global exponential convergence to the origin. And the most important observation on this slide is that if I keep here the state x constant, you can see that this becomes something that is linear or whatever, affine in control. Good. So let's remember that from here. Something very similar for safety, same type of system, control bounds. Safety here is defined as the forward invariance of some set. So safety means staying inside the set, described by a differentiable function B. A sufficient condition for safety is that I can find a controller U that satisfies the control bound and this inequality. By the way, these are lead derivatives. I guess you guys know that, right? I have a scalar function. I want to see how the value changes along the vector field. I take the dot product between the gradient and the vector field, right? Okay, and again, what I want you to remember from here is that if I keep the state x constant, and if I want to solve for the control, here is this is linear in U, right? So it's just a linear inequality in U. Okay, so I want to put these two problems together. I want to now to control that system. It has control bounds. I want to minimize energy. I want to achieve safety and convergence. Based on what I showed you so far, I can map this problem to a nonlinear optimization like this. I want to minimize this cost subject to all these constraints. The dynamics, the input control constraints, this one ensures convergence, this one ensures safety. That's a hard problem, yes?
Like this looks like a stabilization problem instead of a reference tracking, right?
Yeah, but again, remember I said, let's assume that my trajectory tracking is solved by converging from one waypoint to another. So I'm making this assumption, yeah.
It's not the same as the top. It's more conservative, right? Because
it is more conservative, right?
Safety.
Right. These are all sufficient conditions, right? So it's not a one. It is conservative. Okay. Good. And it's also it's bad, right? So solving this, I don't think it's good news. But again, some people thought about it and they came up with a very computationally efficient algorithmic approach to this. And that's kind of, it's going to exploit those two observations that I made before. Remember the two linearity observations. So rather than just solving this from 0 to t and solving one big optimization problem globally from beginning to the end, what I'm going to do, I'm going to take the time interval that I'm interested in, 0t, cut it into pieces, let's say uniform pieces for now. And then I'm going to solve this problem in each interval. So let's say at time 0, I'm here, I have the initial state, I'm going to keep it constant. If I keep that state constant, then this is going to become a linear inequality in U. Linear inequality in U, I'm going to assume that U is polyhedral. So far, all these three are linear constraints. Good. And then I'm going to minimize this, right? So I have a quadratic cost, linear constraints. That's very good news. It's a QP. I'm going to solve the QP. I'm going to find the solution U. I'm going to apply it at time 0. I'm going to keep it constant. I'm going to integrate my dynamics forward in time. And I'm going to end up at the next state. And I'm going to reiterate. Right? So if I do this, I'm going to replace one global ugly optimization problem with a bunch of very myopic QPs.
The second version is kind of a greedy, actually greedy policy for your general optimization problem. Is there any divergence, possible convergence guarantees between the big program and the smaller ones?
So there's I can have a long answer and a short answer. Short answer is no. It's this is actually very and it was designed to be like this, and we have people actually who understand this problem very well. It was designed to be computational, right? But if you cut it into very small pieces and you put it into, I guess, bipedal walking first, it works. But it's obviously conservative, right? So you basically lose convergence, lose safety. Theoretically, you don't have those guarantees anymore. But you hope that if everything is well behaved, it's going to work. Okay. All right. So I'm just very briefly going to show some work from my group on how to address limitations of this original approach. So in the original approach, the way it was designed, it only worked for, I would say, a system with the relative degree 1, right? So this relative degree is kind of, actually, I can illustrate it through this very simple example. So assume that I have a one-dimensional unicycle. So think of this being ego is supposed to follow some preceding car. And the dynamics are given there, and the safety constraint means maintaining a minimum distance of delta between the preceding vehicle and ego. And again, you wanna, so that's safety, right? So you're gonna formulate a function which captures that. So that's gonna be this B function. So I'm gonna require this to be always positive. So if I go to this equation and write it down for this particular case, if you're familiar with input-output linearization, this problem happens a lot, right? What's going to happen is that when I compute this derivative, the control is going to disappear, so that sufficient condition becomes useless, right? So how do you deal with this? So that's something that we've been looking at with one of my students, and apparently it turns out that if you have a relative degree m, which means you have to take m derivative of your, again, in the input-output linearization jargon of the output function until you actually see the input, so that's relative degree. If you iteratively define m CBF type functions like this, then you can come up with a sufficient condition very similar to what you had before, which looks a little bit more complicated. It's a bit more conservative, and the guarantee is a little bit stronger, right? So think of each of these functions defining a set like before, and this C1 is the original set that you're interested in because size 0 is actually the B function that you used to formulate your original safety problem. So you can ensure the forward invariance of the intersection of these sets, and implicitly of this one that you're interested in, if you satisfy this condition, right? And it looks a bit more complicated. I'm even omitting something here which looks ugly, but you can find it in papers. But again, the good news is that computational-wise is the same problem as before, in the sense that if you keep the state x constant here, you still have one linear inequality in U. You can still chop your time interval, and you can still solve a bunch of QPs to solve the problem from before. Again, I'm going quickly through this. Again, though some of you here are experts on this, is just like a refresher. A more interesting problem is feasibility, right? And those of you familiar with this technique, you always run into this. So remember, initially I have one global optimization problem. If I had like a very strong computer, I would solve that, but I don't, right? This approach in which you cut it into pieces and solve QPs is very myopic. So think of, if you're here somewhere and the state is fixed, then you solve your QP, which is very fast. It gives you a control. You apply the control, then literally just apply that control, and you're kind of not seeing anything, and the system is going to evolve to the next state. When you get to the next state, it's very possible, or it is possible that if you plug this that new state into the constraints, you end up with an empty set, right? That state does not satisfy the constraints, and that's most probably is going to happen because of in practice, it happens because of control limitations, right? You get into a state and you don't have enough braking power to actually get there. And by the way, the constraint at the top, which is stability, most of the time we relax, when we slack it. It's not like in our autonomous driving problem, if I don't go like precisely to my waypoint, it's okay if I'm just close to it, right? It's still going to be okay. And this way, okay, so the way to do that I'm showing here, but there is a delta there instead of the 0 at the top and some delta squared in the cost. So that's usually not a problem with the feasibility, but safety and control constraints are problems. And there's many ways you can deal with this, and there's from different groups, different approaches. I'm obviously very biased here on my own work. So one way is to actually exploit the structure that we just introduced for high order control barrier functions. So the constraint that we have here was that this whole term here is a class K function, which is a pretty large class. And then what we can do, we can introduce extra degrees of freedom in our problem. We can put some penalties in here or weights, and then we can design dynamics for it. And then, so basically we're introducing degrees of freedom, extra dynamics, but some extra constraints, which again will be extra CBF constraints. So the optimization problem becomes significantly larger, but you can show that it becomes significantly more feasible because of the extra degrees of freedom that you have. Another way, which is actually very intuitive, is to kind of learn feasibility, right? So think of your robotic application and you move in a cluttered environment. There's many, many, many obstacles. And let's say that you have some time to do some computation before you deploy your robot. So one thing you can do, you can just go get close to the obstacles that were most probably you're going to become infeasible when you solve your problem. And sample. So let's say that you generate many, many, many samples around your obstacles. And then for each sample, you can go plug it into the set of constraints and see whether that's feasible or not. If it's feasible, you're going to label it as feasible. If it's not feasible, label it as unfeasible. And you had 10,000 of them. And then you can build a classifier which separates feasible from unfeasible. And make sure the classifier is differentiable, right? So then I'm going to introduce an extra constraint in my problem, which is going to say that that classifier is positive, for example, right? So I'm adding a constraint in my original problem, which makes sure that I'm never going to get into this infeasible states, right? It's very ad hoc and very heuristic, but it shows to work. And actually, we have a paper which shows that it works in, like, for example, it has some nice invariance properties too. Like, for example, if you look in a sphere world where you have sphere obstacles, it can be actually very, very cluttered. And you can just solve one optimization problem and then just keep on translating the solution everywhere. And you can get, I cannot see my, okay. Okay. So you can, you can literally move in very, very cluttered environments, which for those of you working with CBF, CLF, it's actually kind of good because, you're in situations like this, you usually lose visibility. Yeah.
So when you say you're solving a single optimization problem, is it offline? Like you put all of the constraints and you have to solve it offline, or are you solving it online?
You solve it offline and then translate the solution depending on the position of this and the sizes of those. Yeah. But you can discover them online too. So I'm not sure if my answer is actually complete. I'll have to double check. I think there's an online version of this somehow. Yeah. Yeah.
Can you generalize this such constraints to any kinds of obstacles?
You can play the motion planning game, right? Apply some diffeomorphism, make the sphere world, like the classical navigation examples, This was from Kodicek when he was here, right? Right, so you look in a sphere world and then you apply diffeomorphism and then deform them diffeomorphically in the way, that diffeomorphism most probably is going to preserve this. We never looked into that, but I think there is a way, which might be computationally very hard.
It looks like the animation has dynamic obstacles. So are you doing a classification? Like, is the classifier learning for a sphere?
Yeah, so that actually goes back to what Mika said. I think there is an online version of this because we deal with them moving around. So I think this robot looks, I think you can even see it. You see, you see the robot has a local sensing range. So it looks around it, and once it identify an obstacle, it knows how to automatically generate the control laws by translating the control that it had at time 0.
But you have learned your parameters offline. That's what you.
Oh, you're talking about this? Yeah. Learning is done offline, of course.
I'm still a bit confused.
Yeah.
Are you suggesting you're learning the barrier function?
Learning a classifier for infeasibility.
Usually the feasibility is deal with the barrier, right? It's kind of
Yeah.
like your constraints
Yeah,
encoded in the
yeah,
barrier.
but so this is a bit unintuitive, right? I mean, if you have an optimization problem and if you keep on adding constraints, what do you expect? To make it less feasible. But it actually, if you think a bit deeper into this CBF thing, you can actually make it feasible, because infeasibility becomes here because if you're myopic and apply a control and you all of a sudden end up into something that's unfeasible. But if I had a constraint steering me away from that, I might actually stay feasible.
It's kind of like you have some barrier function, but it's not the true barrier function. Then you're adding.
So the barrier functions for here are to avoid these things. But what I'm doing, I'm introducing extra barrier functions which actually don't let me get close where I can become infeasible.
I see. Okay. Thank you.
Yeah, but your constraint is small, no convex, is instead of polytope or convex, where it make your.
No, this U.
No, I mean this figure, no convex.
It doesn't have to be convex. It's differential. Does B have to be convex, Mika? It doesn't have to be
I
convex.
think that they mean in terms of convergence to a destination, you could probably get stuck in local minima depending on how
Yeah.
it looks like.
Yeah.
But in terms of safety, you should be able to remain safe. Probably you will get stuck though.
Yeah, you can, again, there's no guarantees of, what you can show here is that you can improve feasibility. Yeah.
Hi, are you computing the CLF and CBF sequentially, or are you considering to combine them together to do a control Lyapunov barrier function? I mean, a barrier function can be a sublevel set of Lyapunov function. So
Yeah, and we have work on that. There's also some work on that in this. Like for example, control barrier functions are good, at least in their original definition. If you start inside the set that you want to make invariant, right? What happens when you start outside? Then you use the combination of a Lyapunov, a CLF, and a CBF, which actually would make you, during your group, there was a discussion about that, makes you come inside and then becomes like a proper CBF. We even have a paper which you classify them somehow. There is a CBF of type 1, CBF of type 2. There you also have something which you call a Lyapunov barrier function. There's so many versions of that. Okay. All right, and I would say another limitation is that whatever we showed before works for the case when you know the dynamics precisely. What happens if you don't? And again, the simplest thing we can do, especially if we come from control theory, would be to look at the framework that people use in adaptive control. So introduce some uncertainty, but very structured. Some unknown parameter acting along given control directions and known to be in some set. The question is, can you extend this, right? So what I'm showing here, it's a sequence of QPs that you solve very, very fast and you ensure stability and convergence. Can I do exactly the same, have a sequence of QPs that ensure stability and safety in this case? Right, and it's a longer story, but the answer is yes, but you have to spend a little bit more, you actually have to do more computation. So I'm just showing you here kind of what the algorithm does, right? So remember, in the original version, you have to cut your interval into pieces, keep some state constants, solve QP, apply, integrate one system of differential equations, go forward. In this case, you have to define some extended version of the CBF, extended version of the CLF. And this is what you do at every iteration. Every QP becomes significantly larger, but provably correct. I'm not going to show details, but if you want to just stare at this a little bit. Okay, so again, the quadratic control, the condition for stability is at the top. Right below is the condition for safety. So again, we discretize the time again. We start with some initial state. Start with some estimate for the parameters, right? And then solve the and then solve the QP. Solve the QP there. This is the whole. Okay, so you have to maintain an estimate for the parameter, right? So basically what you do, I think I'm going a bit too fast, Nico, I forgot to say something. So again, this is more like what people do in adaptive control, right? So in adaptive control, you take a measurement of your state at every time. So the question is, if I take that measurement of my state, I can actually maybe get, since I know I know the structure of my dynamics, I can get some information about the parameter at every time step. Right, so and that's shown here. So this function is known. This is known, right? Because you know the control that you apply, you know the state that you measured. This one you can either measure it or approximate it from small differences. So this is known. So at every time step, I have something like something known equal to some known matrix multiplying your parameter. So at every time step, you get a linear constraint on your parameter. Good. So the question is, how can I use this to maintain estimates of my parameters? And the way we do this, and I'm very bad at citing the paper that we got this idea from, but it's you actually you can show that you need to maintain a history of all your measurements. There is a stack of data that you have to maintain. At every time step, what you do, you collect one of yi's and psi's, which are these guys, right? This and this, you can collect them, put them in that stack, and at every time step what you do, you basically have to solve a QP and then integrate forward all these differential equations in addition to the one that you had before. Yeah.
This assumes that theta is constant, right? Can't be time varying.
Theta is constant. We assume it's constant, right? The estimator varies in time, but there is a
Because you're taking all the past data and
right. There is a known constant. There is an unknown constant value of theta which we estimate. Yeah. And again, without going through the math, I just want to maybe emphasize some interesting points and kind of intriguing points. The fact that we actually have to maintain two estimates of the parameter, one for the CBF and one for the CLF, to ensure safety and stability. These are the two equations. Another thing that you might recognize in here that, so again, I have a bunch of linear constraints for theta, right? So the best way to find theta is to use some least square approximation. And that's what we're doing, really. You can recognize these least square terms in here from the data, right? So that's another interesting point. And there was a question? Mika.
Do you have any assumptions about persistency of excitation of the signal so that you can
Not anymore. No. And again, I'm apologize for not referring to that word, but there is no. We don't have that assumption.
Yeah, but is it because you don't care, like, to converge to the actual value of theta?
There is what we have is, I'm not sure if that's the same, but we have a condition on the rank of these matrices. This has to be like full row rank or something like that. That's not the same as persistence of excitation.
Yeah, or I wonder if you care about essentially not identifying explicitly theta, but rather like the linear form phi times theta or however.
Right.
Because if it is like
Very
a
good point.
disturbance that you want to identify, then you just care about that.
Very good point. So again, so what we also, so the difference from this method and the persistence of excitation that was trying to hide under the rug is that in this method actually ensures convergence to the truth value of the parameters, which the other method does not. So we do converge to the true value of the parameter. You can show that. And you can actually kind of see it from here. So again, what I'm showing here is an inverted pendulum. I think the most interesting part to look at is here, where you can actually show that you see you have estimates for theta 1 and for theta 2, two estimates, because I need two estimates if you look at the math. But they both converge, they become the same, and they both converge to a value, and that happens to be the true value of the parameter. Another way of thinking here, which is not that intuitive, is that we actually have to also construct an estimator for some sort of an upper bound of the CBF to make this whole thing work and ensure safety. And this is work done by Max Cohen, if you guys, some of you might know him, he's in Caltech with the Arrow now. Yeah.
Sorry to bombard you with questions.
No,
but,
please
but
do.
we're interested, right?
Jeff was asking about the assumption that theta was constant. I was interested
Yeah.
too, within your data stack, each of those y values there contains a measurement that's based upon a measurement of a derivative. And
Yeah.
so presumably there's got to be some filtering that you do.
Yeah.
How do you have a sense of how strongly you need to apply that filter? And if you're in a case of a slowly varying theta,
Yeah.
that you need to identify quickly enough in order for your identification to be relevant, is there a conflict that
Yeah.
arises?
A very good question, but I don't know. We don't know. But it's I think there should be something, but we only assumed it's constant, and we never looked into that, how to actually filter it and make sure, if it varies, we can still estimate it. Yeah.
Another good question. So you've got a theta that is a fixed number in your dynamics there. So
Yeah.
why do we need two different thetas when we go to CLFs and CBFs?
Because of the conditions that we need to satisfy to ensure safety and
And you get to the true value of the theta, you should
Yeah.
be able to use the same theta to compute.
No, but I mean, I have to. This is how I'm integrating my state, right? And in order to ensure, so it just happens that in order to ensure safety and so by using CLF and CBF to ensure stability and safety, we use different. We need different equations for theta hat in order to show the proofs work. Both equations, so they both of them converge so to the same value. Yeah.
For the second to last formula, update the worst case bound for CBF.
This.
Yeah. So you just mentioned you need to make sure this matrix has some full rank thing, right?
It has some, yeah, actually, yeah.
So does that mean as long as it becomes full rank, then you don't have to collect more data?
No, you still have to collect more data. If it loses rank, the method fails.
But as long as you have already make sure this.
No. You still have to. So staying full rank, it's fine, but you keep on adding information to a full rank matrix, and this one still evolves in time. It's not like you're solving a one inversion, and if it's full rank, I can invert and then I have unique solution.
I see.
I have to keep on adding data from the stack to this, and this one still changes in time. I think this has something to do with the persistence of excitation, like the lambda means something, if I remember well. Yeah. All right, and we can make things more sophisticated with the law of conservatism, but very intuitively. So now let's say that I want to extend CBF/CLF to full LTL. Is that doable? Yeah, but conceptually, so let's say that you have a formula which says that you have two regions, so 1 and O2, and you want to visit them infinitely often and always avoid this one, right? So that's an LTL formula. I told you that every LTL formula translates to some sort of an automaton. So basically, the sequence of O1, O2, O3s, these are infinite sequences in time. The sequences, infinitely many sequences that satisfy this formula are the same sequences that are accepted by this automaton. And remember, automata have acceptance conditions. I have to visit a set of final states infinitely often. So this is how the automaton looks like. So now really the question is, how can I enforce that my system produces executions that are accepted by this automaton, right? So basically, I just want to make sure that my system goes from generates symbol O1 and then never generates symbol O3 and so on, right? So if I want to generate symbol O1, which means that I'm visiting region O1, I'm gonna solve a CBF-CLF problem where I have a CLF function that takes me to region O1, right? So the CLF is for convergence here. And a CBF function that makes sure that I don't take this transition that would take me to a trap state, which would violate the acceptance condition of the automaton. Right, so okay, maybe easier. So let's say that I start from here somewhere. At this point, I'm going to solve a CBF-CLF problem in which I have to integrate, dynamics x dot equal to f of x plus g and x and u, and then the control constraints. And the CLF would be a CLF which would take me here somewhere. And the CBF will tell me that this region is forbidden. And how do I solve that? Again, I chop things into pieces and I solve a QP. Okay, now if you want to be a bit more formal, okay, how long am I going to solve this problem? Well, until I reach this region, right? So if you look in this paper, for example, we have like a hybrid automaton in which we have guards on those transitions. So I'm going to solve that CBF-CLF problem until the guard is satisfied, which means I reach this and then I switch to something else and so on. So again, it's very conservative, but it's, you can show that this approach is correct. Questions on this? Again, very conceptual, right? CLF take me to places, CBF keeps me away from places, which means that I can enforce taking transitions versus not taking transitions in an automaton, and automata give me the richness of a temporal logic. All right, so let's go back to my motivating problem. Remember, I want the car to follow a set of waypoints, and I'm going to use CLFs for that, and then I want to satisfy a set of priorities, a prioritized set of rules. Each rule is going to be a CBF. And how am I going to deal with the priorities? So the simplest approach, and that's exactly what we did in here, was to have a very greedy approach. So I'm going to try to see if I can satisfy all the rules from the priority list, right? And that's going to give me a bunch of safety constraints. Try to solve the problem. If I cannot, then I'm going to have to start relaxing constraints, right? Because I want to have some sort of a global minimization of the set of rules. And obviously, if I cannot satisfy all the rules, then what I'm going to do, I'm going to try to start to relax rules that are not that important. Like, for example, satisfying mean speed limit, it's not that important. So I'm going to allow that to be violated. How we do this formally, we select the corresponding constraint. Right, so here's at some iteration I have some rules which are relaxed. So I put a delta I in there, and then I penalize it in there at the top. Good. And also, as I said, the convergence to every waypoint, the CLFs are always slacked too. So I don't have to have extra constraints giving me feasibility problems. That's kind of it. Make sense?
You have a predefined set of priorities.
Yeah, and it's also, there's also like discussions we can have in here. Ours is a total order, so it's kind of very easy to, if you have things, some priorities which like partial orders, those are harder. We have some results on that, but I think intuitively this is enough. So there's a total order. And these are the kind of results you can end up with, right? So for example, here's a scenario in which you have the ego here, and then an active vehicle that moves this way, 2 parked vehicles here, 2 pedestrians. I want to solve the problem, right? So what happens again, we try to satisfy everything, we cannot, and then we relax starting from here, and we end up with a solution that looks like that. So what I'm showing in there is that blue portion of the trajectory violates one of the rules, which happens to be R5, which happens to be the lowest priority one. So apparently I have to slow down under the speed limit to be able to satisfy the set of rules, which might be a bit unintuitive, but this is because what happens in here is, the way we do collision avoidance, we put a bounding box around ego, and the size of the bounding box depends on the velocity, right? So the faster I move, the longer the bounding box is to make sure I'm safe. So apparently I have to move very, very slowly at some point to make sure the bounding box is small, so I have enough space to kind of go in between pedestrians and stopped cars and so on, right? So that's why that's violated. And again, but that's all done automatically. And I can have, more complicated situations. So I look at this one, for example, when I have to do this kind of maneuvering. So obviously here I have to violate more. So we violate here lane keeping too. I have to get out of the lane, right? And I'm showing, portions in which I violate different types of rules. But again, globally, I'm minimizing violation. All right, that's half of the talk. So very briefly, actually, it's okay. So very briefly, I just want to show you some, again, we're going towards more like machine learning approaches. So here's the problem that we looked at. Some of you might recognize Baxter in here. This is actually a simulation environment. And I have the task of grabbing a box from one place, putting it to another place, and avoiding some dangerous region. And the specification, again, is rich as before. Different type of richness, so you can see that now I actually have concrete time constraints, like I want to do things within certain deadlines. Right, so again, given the time is short, I just give you like a very, very high level overview. So again, all we assume, so again, Baxter has 45 degrees of freedom. It's a very, very complicated robot, right? So using the actual kinematics or dynamics, it's challenging. So it makes sense here to use some sort of a combination between machine learning and control. So we only made an assumption here about the structure of the dynamics. So we assume that the dynamics are of the type F plus G of XU, which we know every single manipulator satisfies that. And then what we do, we start learning. So we learn F, we learn G, and then we learn control policies given the model that we learned at a particular iteration. So literally what we do, we just start moving the robot around a little bit. Okay. The most important thing is that the logic that we have here has something called quantitative semantics. In the sense that, so that's STL for those of you familiar with this. So this logic has the property that once I have an execution, I can actually quantify how far that is from satisfaction. So I have a number which tells me how good I'm satisfying. And I'm going to call that measure of satisfaction rho. That's called robustness. Okay, so what I'm doing here, I'm going to start to move robot around a little bit. I'm going to get a very preliminary model, like some estimates for the drift and for the control directions. And for that, and again, we're using neural networks for each of them. It's like FNMs here, what we do, we minimize the error between the measurement and the predictions of the very preliminary model that we have, right? So we have some very preliminary model. For that model, we learn a policy. How do we learn the policy? We're doing by maximizing satisfaction of the spec, right? So the spec tells me to pick up something from somewhere, drop it somewhere, avoid the bad region. For that, I can formulate a measure of satisfaction. I want to maximize the measure of satisfaction. And also, rather than just using simple FNNs in here, we actually have to use recurrent neural networks. Because satisfaction of STL requires memory. So this is, RNNs have their own state. They can capture history, which is necessary for STL. Again, some of you are familiar with that. If you don't know, I can tell you more on the side. But what's really cool in here is that, it turns out that we were actually very surprised, like how fast we can learn with this approach. Literally, like we did like 5 cycles and like in 14 seconds, learn the perfect policy. All right, but again, there's no proof. So we published this in ICRA, it looks very good. Intuitively, it makes sense, but, and maybe just one more idea. I have 1 minute. So this is like way more complicated, right? So we have this framework in which we wanted to have to like cook, right? So we have 2 robots, Jaco and Baxter. This is a real experiment. They're making hot dogs, which is a complicated task. So the question is, can you specify, tell the server what to do, tell the cook what to do, specify a lot of general knowledge, like for example, don't grab the hot dog if it's not cooked, or if you cannot grab the hot dog if the gripper is closed. Like these kinds of things, like tell the system as much as you can before it starts doing, brute force reinforcement learning. Does that help? And again, what we use, we use another logic, but again, a logic which accepts automata. So we can have like a bunch of specs and a bunch of general knowledge. There is a way to write them down formally and automatically generate automata. And the automata can be composed together. And then for those types of automata, we can also define a degree of satisfaction, which kind of depends on how we satisfy some predicates, like closeness to things, but also kind of how far we are from reaching a final state, which means how far we are from actually accomplishing the task.
So that's like the degree of satisfaction is like the reward that you would give in a reinforcement.
Exactly. That's what we use to shape the reward for reinforcement learning. which is different from before. Before we had something way more structured, the robustness of a logic. Here it's basically when you move in this automaton, you kind of have an idea of how far you are from a final state, but also you have some predicates in here for which you can actually also measure how good you're satisfying them. So, if you look in the paper, there is a technical part which explains this. But again, long story short is that you can put a lot of information at the top, specifications and general knowledge, generate a big automaton, start doing reinforcement learning in here. And as Mika said, we use this to actually shape the rewards and reinforcement learning. And then what happens in here is that there's another trick in here, like, you can show that the reinforcement learning actions that you get from this messy learner here, you can also project them to a safe, you can solve an optimization problem. You want to be as close as possible to the output from the RL to generate a control that's safe in the sense that what we did with the CBF. So the CBF, but it's have like a bunch of constraints and you solve an optimization problem, which happens to be a QP. So you can always do a projection at the end to stay safe, deviate a little bit from the RL, so learning might not be as good, but it ensures safety. So I guess that's all I wanted to show you. Anyway, we can look at the movies. I would rather show the people who did the work. Only one is in my group anymore. This guy is going to be on the market soon. And these are the movies.
That's the last slide.
I'm done.